Good morning guys, in this video I want to talk to you about LEDs. Now it might sound very basic and simple, and perhaps it is even, but before I could really go into 7-second displays or any other display technology, I wanted to start at the real basics of an LED. And I'm going to be mainly focusing on how to wire one up, how it works, how to differentiate different types, what kind of resistors to use, how to get data from the game and display them on our LED, not on our LED, but with our LED. So it's really going to be an in-depth look into the most basic component, or perhaps is an LED. For those of you that are waiting for the update for the connector, it's almost out. You guys have been sending lots and lots of bugs reports since the last refactor, and it's amazing because it means that more and more people are using it and more edge cases are being found. And they are being fixed, so it's almost at a stable state where I'm confident releasing it without having too much edge cases that could lead to certain crashes or infunctionalities of certain topics. So that's coming up. Stay tuned. Very soon, few days. Now let's get back into LEDs and see how they work. Now, if you get lost anywhere during this video, I'll put a link to the article that's written out all the topics that I'm going to discuss. It's on my website. The link will be in the description down below. Now, I could just grab a normal LED and start showing you things, but I think this is going to be a bit more easy to visualize what an LED does, how it works, and how to wire one up. The first thing that we need to differentiate is that there are all kinds of LEDs, right? We have like with 4 legs, which are usually RGB LEDs. We have these standard diodes that have 2 legs. You have the ones that you solder onto a board. We have LED strips, etc. Today we're going to be focusing on the real basics of LEDs. So that's going to be the normal LED that we all have seen in various applications. And we're going to be using the RGB LED. Now, first of all, the thing that I've known way too late about LEDs is that they have a positive and a negative side. The positive side is also called the anode, and the negative side is called the cathode. It's important that we power the LED from the anode and that we let the cathode run to ground. But how can you see which one is which? Well, usually it can be seen on the size of the leg. So if you take a look at this one, if you would bend this straight, which they usually are, let's see if I can. I can't, but this one is usually longer, so we know that this is the anode side, or the side where the power has to flow in. The other side, the shorter side, will be the cathode side, where it has to flow out. Now it can also be spotted by, if we take a look at the LED itself, that the lead inside, if you take a really close look, you'll see that there are some leads inside. The biggest one is usually the cathode, so they're going to ground. This is especially important when we take a look at RGB LEDs, and perhaps even if we start looking at RGB displays, etc. in a later video. But for right now, in the RGB displays, in the RGB LEDs, we have 3 legs. 1 R, G, and B, and they have a 4th extra leg. Now there is a chance that it's a common cathode or a common anode device. And I might think to yourself, Dave, what the heck is a common anode or a common cathode device? Well, these leads, the R, G, and B, either share the power coming in over the same line and they have their own power going out, so the cathode sides, or they have their own power coming in over the wires and have their own power going out, shared power going out over the common cathode. The most RGB diodes you will find are common cathode. This means that we have to power the R to get red, we have to power the G to get green, I have to power the B to get blue, and they share the same ground pin. I hope that that was a bit clear. I know that for me, I usually just plugged it in and I was fine to go, but there is an important difference to be made on how you wire them up and which pins you provide power and which pins you wire up the ground. If you've got an RGB LED, it's important that you take a look inside to see which has the bigger lead. If there is a bigger lead going to the second pin usually, we know it's a common cathode. If all the other ones have bigger leads, we know it's a common anode. Well, an RGB LED can create quite a broad color spectrum with the RG, so red, green, blue. Because if we mix them together, we can make almost any color we'd like. And the more of one color we put in, the more blue we'll get. The more we mix some blue in with green, we'll get purple, I believe. If we lower the blue or the green, we'll get more pinkish color. So we can really play around with it to create the color that we want. Now, if we take a look at the test setup we've got right here, we're able to tell that they aren't wired directly to the power line. As we're hopefully able to see, they are wired up to a resistor and one wire going to the ground like we mentioned before. Now, why do we use a resistor? Well, it's quite simple that if we would remove the resistor, I'm going to show you actually. So we got a wire going into towards ground, and we're just going to directly wire to the 5 volts line, and it's done. See, we're able to tell the LED already died. Let's see if it's hot. No, it isn't, but I'm going to take it out. If we just wire it up to the 5 ground directly, most of the times it will burn the LED and it won't be usable anymore. Now, how can we stop that? Well, it's quite simple. We add a little resistor from the power line to the LED. Here we go. And if we now add it, it will keep on shining bright until the day it dies of old age. So that's a significant difference, and that's the importance of picking the right resistor. Now, the stronger the resistor is, the more brightness is going to be taken away of it. Let's see if we, for instance, this is a 570R resistor, and I'll come back to that in a second. This is a 1K resistor. As we're able to tell, the light is significantly less bright. And this is a 4.7K and it's barely lit at all. Now, how do you know which resistor to use? Well, there is a minimum value we need, right? And there is a simple calculation that we can use for that. It depends. It's quite simple actually. I'm going to show you. Its resistance is the voltage of this voltage supply minus the voltage of the LED forward voltage divided by the current that runs through the LED. Now, this might seem daunting, but there are some simple calculators online where you can just enter these values. Now, you might think to yourself, but I don't know those values. I don't know the forward voltage. Well, usually if you buy a set of LEDs, the supplier or the seller will actually give you the data you need. So let's see, in this particular instance, here we go. The forward voltage, yeah, okay, this is in Dutch, but it says forward voltage, red 2 to 2.2 volts, and blue 3 to 3.2 volts, with a power strength of 45 milliamps. Now, if you would just pass these values all into this formula, we would get something like 290, 180R resistors usually. It depends a bit on the color, because the white, blue and greens actually have a higher forward voltage than the red and yellow. So that can differ a bit, but you would get something around 180, 200R. Now, if we would take a 180 or 200R resistor, the LED becomes quite bright, and it wouldn't be really pleasant to look at for a longer prolonged time, especially have it inside of a flight panel or something. You don't want it to be that distracting that you're like, please turn it off. Perhaps if you have an alarm, you really want to bother yourself, that's fine. But like I mentioned, it's a minimum value. So what we could do is that if this is a bit too bright, in my opinion, 200R, so we just take it out and we add something like 500R, and this is way more softer on the eyes and way more comfortable to look at. So that's something to test around for yourself to see which one is best suited for your own use cases. Now, if we would swap this one out, if we swap this out for the blue one, we're able to tell that it looks quite a bit brighter, and that's due to the difference in color and the strengths and the current that runs through it. So it's important to, even if you have the same LED but with a different color, that you take a look for yourself which one is best suited for me. Now, as long as you stay above the minimum value, you're all fine. Okay, I hope you're able to see how I wire this up. So we got our ground line, which goes to a common ground line, as we are able to tell. So the cathode side, so the smaller leg, goes to the ground side, and the power, which comes from a digital pin or an analog pin for that matter, goes to this row. Then it goes through the resistor to make sure that the LED survives, and then from there on out it can pass through the LED to the ground. Now, if you just want to turn it on or off, we could use any pin on our Arduino board. We can use it on any digital or analog pin on our board. Now, if we want to determine the strength as well, it's important to differentiate certain pins from other ones. So if you take a look at this Arduino, we're able to see that there are about 13 digital pins and 6 analog pins that we can use to turn the signal on or off. If you just want to use that, you can use any pin. If you want to control the strength, we need to use a pin that has these squiggly lines in front of it. So 3, 5, 6, 9, 10, and 11. Now these squiggly lines, it already says it on the board most of the time, are the PWM pins. PWM stands for pulse width modulation. With pulse width modulation, we can alter the brightness of the LED. Now, it's a bit confusing because to use this, we're going to use the analogWrite function. Why is this confusing? 2 reasons. A, you can't use any analog ports for this, so you can only use the 3, 5, 6, 9, 10, and 11. And B, it's not really an analog signal that gets sent. It sends a wave of on or off states depending on how bright you want it to shine. So at 255, the wave will just be on all the time. At 0, it will be off all the time. And in between, it will depend on which value you've selected, if it will go on, off very rapidly or very slowly. This will change the perception of the LED and the brightness we see. So it isn't really lowering the power, it's just changing the rate at how fast it goes on or off. This is a really fine-tuned wave, so optically we aren't able to tell that it flickers all the time. In code, we can actually see, if we would measure this, that it would just be an on or off signal going towards our LED. So even though it's analogWrite, it's not really analog. And even though we say it runs not as bright, it kind of doesn't. So that can be confusing when you encounter this. And even for me, I thought that the analogWrite could be used on the A5, A0, and A1 as well, but it just isn't the case. Now, let's just write up some code to actually see how this works in reality, right? Now, I've hooked up 2 LEDs, one towards a pin that is PWM enabled, so 3 in this case, and 1 pin that's just a normal digital pin. Now, in order to code this up, I had to make some room for my keyboard. So in order to code this up, we're going to first define where our pins are connected. So we say LED yellow, so we know which LED we're talking about. It's going to be hooked up to pin 3. And we're going to define where our red, no, let's be consistent, let red is connected, it's going to be 2. So the yellow LED is PWM powered, enabled, and the red one isn't. Now what we could do is very simple. First we need to define what our pins are. So we say pin mode. So not really what our pins are, but what functionality they have. Are they inputs or outputs? But in this case, we're going to say that yellow is an output. Because an LED will never send a signal back. It will never be end pressed to see if it's touched. It will just receive a signal to turn it on, and it will receive a signal to turn it off. So we do the same for the red. LED red is an output as well. Now to turn it on or off, we could say digital write. Now the yellow pin was PWM enabled. So I'm going to say, first we're going to do digital write on both. I'm going to say high. And we're going to do the same for the LED red, which is going to be high as well. Now, if it's high, it's going to send a 1 or 0. So ones and zeros are digital write, just like a computer, all things in ones and zeros. So we could even put this up here, because we only want to execute it once and it will stay on. But it will turn the yellow on and it will turn the red on at a high state, so the on state. Now, if we had uploads to the Uno, we see both of them are turning on, exactly like we expected. But for the yellow one, we could do an analogWrite. So we say LED yellow, so the pin that we want to write to, and we could pass it a value between 0 and 255. 255 is fully on, 0 is fully off. So let's just test around with 100. Well, to be quite honest, I don't really see the difference, but that could be me. No, you can see it's noticeable. Perhaps even if we lower this further to 10, we'll see, yeah, it gets really, really dim. So if we put this at 0, it should be off. Perfect. So we can really control the brightness and intensity using the analogWrite. The only downside is you can only use this on the PWM enabled pins. So if you would try this with the LED red, see, it won't do anything because it isn't PWM enabled, this pin. It won't put it at a certain brightness, it won't do anything, only if we use the digital write. So it's important to note for when you code the LED up, that you use the proper pin and the proper mode depending on which one you want to use. Now let's say we want to get some game data, shall we? So let's do hashtag include. Here we go. Bits Androids flight connector.h. Long word. So we included a library like we usually do. We've created an object called a connector. Now to receive data, we're gonna do something in the loop. We're gonna say connector.data handling. This will ensure that on every loop, it listens to the COM port if new data has arrived. If that is the case, it stores it inside its corresponding variable, and we can use that later on to see if a light is on, a state is on or state is off. Okay, still following along. So let's say if something is true between these brackets, we're going to execute the code block in between. So if, let's say, connector dot get AP master on. Let's see if that's is the right one. No, it isn't. AP. It was. I made a typo. Get AP master on. AP master on is a boolean. Now, how do I know that? In the documentation, it is defined in a column. If it's a boolean, it says boolean false is off, true is on. So get light taxi on, we know that that is a Boolean returned, and a Boolean is nothing more than a true or false state. Now this code block only gets executed if what is between these brackets is true. This Boolean is true. It will execute the code block. If this Boolean is false, it won't. So if the game has sent to our library that the AP is on, the Boolean will be true and this block will be executed. So in that case, if it's true, we're gonna do digital write let red, I like the word, hi. Now else if, so if that's not the case, connector.get AP master on, but with an exclamation mark. So if it's not true, because we did an exclamation mark, so if it's false, we are going to do digital write let red, and we're going to make the signal low. So far we made our first statement that's going to check if we need to turn on or off a light. Oh no, and I still missed the, it's important to add the serial.begin 115200 and serial.set timeout, and let's say 15. This is to do with how long the Arduino is going to wait when receiving data, but I'm not going to go into full depth of it. It's not really relevant. Just know that you need to set it at this and you should be fine. And if all things are correct, the light should stay off, right? Because we didn't turn it on anyway. Oh, we did it in the setup block. But it will turn off here as well. So here we go. Now, if we have the connector, last two videos we've been working on inputs. Right now we're going to be looking at outputs. So it's important that we select the data that we want to receive. And this is to ensure that the game only sends data to your Arduino that you actually need. It would be nonsense to send the airspeed, altitude, everything you can imagine to your Arduino when you only use one or two variables. So that is why you need to select the ones you need. So in our case, we need the AP master on because we defined it in our code. We want to display this. So we're going to see AP master on. It already says here as well that it's a Boolean, so true or false. And we select our board. Let's see, you know. Now, if I hit start, the board is going to reset itself. So it's important that we add a capacitor. This little boy here, I've got a 4.7 UF one. A 10 UF is recommended most of the time, but I got it to work every time with the 4.7. And what we're gonna do is take our board. We're gonna see where the minus leg is. We can see it, usually it's marked with dashes. And we stick that one on ground, or the shorter side in this case, and the other one to the reset port. So now we've got a capacitor between reset and ground. So just to give a quick view, a capacitor between reset and ground. This is very important, or else you won't be receiving any data with the Arduino Uno, Nano, Mega. What else do we got? I don't know. The Arduino Leonardo, Due, and Pro Micro don't need a capacitor. They handle serial over USB differently, so that's why it's not needed over there. But we've selected our data, right? So now we can go back. We're going to hit start. Capacitor is in. And now we can have a look at our plane. I'm going to start her up the lazy way. Okay. That was a bit too enthusiastic. Let's see. How do I turn on the autopilot in this thing? Ah, here we go. Autopilot on, light turns on. Autopilot off, light turns off. See, the logic is quite simple on this one. If something is true, we're going to do something. If something is false, we're going to turn it off. Now, if we go back to our code, we can see that we have digital write. But I'm going to try something else. So I'm going to remove this, See how we're calling high here? What would happen if we enter connector.getAPMaster on instead of high or low? Well, first of all, we're going to upload a sketch. So we're going to stop the connector, remove the capacitor, or else you won't be uploading any code, and we hit upload. Done uploading. Now we place the capacitor back. Here we go. And we're going to say start the connector again. Okay, so I was pretty dumb. Well, not dumb, but I accidentally removed the output line so it wouldn't shine as bright, and I thought something was wrong. But back to where we were. Like I mentioned, we can control it with a command if it's high or if it's false, if it's true. But there is a thing about coding, right? Everything in the end gets reduced to ones and zeros. So high is actually just another front for 1, just as the true is for a Boolean. So if a Boolean returns 1 and high returns 1, for our code, it wouldn't make any difference if we would pass it high or true. It would both be a 1. To be really precise, it doesn't even check if it's 1, it checks if it's not 0. So 1 is not 0, then it turns the LED on. And if it's low, so 0, just as false, which is just a front for a 0, will turn the LED off. So we reduce the code from, let's see, if this, else, if it's not on, turn it off, to just one line, digital write, let read, connector.getAPMaster on. Now we could even do something like this. Let's say digital write, let yellow, and then we say connector.get flaps handle percent to int is bigger than, let's, I don't know, 20. So I forgot to define the pin modes again, but it's fine. I've added them now. AP is on, AP is off. We see that the light changes depending on that state. Now, if we move our flaps up, oh, no, that's not true, because stop, flaps handle percent. So now if we press start, it's also going to take in consideration the handle. So if you move it back up to 0, the light is off. And if we go past the 20% mark, you see 17 it's off, and at 37 it's on. AP on, that one goes on as well. See what's happening? We're reducing our code from if statements to just a single line telling it, because we could break this down to this. Let's say this. We've created a statement inside of this block. So we say connector.getFlaps handle percent to int. Now, getFlaps handle percent returns a string, let's say 80. We convert it to an integer so we can work with this. If you're watching this video and the new update is out, this will actually be an integer itself, so we can omit the dot to int. But for now we need it. Connector.getFlaps handle percent is bigger than 20. This will return a true or false. Now we get back to the booleans. If it's a true, it's going to be a 1. If it's going to be false, it's going to be 0. It's going to be 0, light's going to be off. If it's going to be a 1, the light's going to be on. So it's a bit perhaps abstract, but I think this is way more readable than those long blocks of code where you have all the if statements and whatnot. So if the get flaps handle percent is bigger than 20, so if the percentage returned is bigger than 20, turn the light off on. If it's lower, turn it off. See, I hope that makes some kind of sense on how you're able to use an LED to display simple states. You could even do it if your altitude gets below certain things, trigger an alarm. I'm working on some pre-made alarms in the library as well. That's going to be linked to the G1000, for instance, where it says low pressure or something. The downside is those warnings exist in the G1000, but to get them, I actually have to read the actual manual of airplanes to see at which altitude pressure value it turns on, and then send a command to your Arduino. So that is something that's coming up. It's going to be quite some work to read through all of that to see all the cutoff points, different planes, how to handle that as well. But that's more for the future. For now, we know that we can create our own warnings, our own light states, using LEDs and just a simple true or false statement. Now, just as a quick last point, the RGB ones. Now, what I've done is I've wired up each of the legs to an individual resistor and cable to a PWM enabled pin on the board, right? So we've got pin 1, which is going to be red, is wired up to pin 2, green, which is going to be pin 3, is wired up to pin 5, and then blue, which is pin 4, is wired up to yellow, which is 6, right? Yeah, 6. The second one is going to be the common cathode line, which is going to be going to ground. So pretty simple setup. And let's see how we can use this to display different colors. So if we go back to our code, we now needed to find something else. So let red is 3. That's true. Let's green. It's going to be 5, and hashtag define let's blue. It's going to be 6. So now we need to change this to let green. Just going to copy this line as well. Here we go, and let blue is an output as well. So you have let red, green, and blue, which are basically one diode. Well, they have 3 diodes in there, but one light bulb. I don't know how to call it. But it has 3 pins, each with their individual colors. Now, because these are all PWM enabled pins or capability to send PWM signals, we can actually do something with those values, right? So we could say, we could do just a basic digital write. Let's just, perhaps, why not? I'm going to show you how that looks. To remove the capacitor, very important. Upload it, place the capacitor back. Here we go. So now we're back in our game, right? We're going to restart the connectors. We're going to start. And right now it's red with green-ish. Now, if we move the flaps down, here we go. If we turn the AP on, it's going to be really, really green. So that's how we can mix colors to display different states. Now we could really fine tune it by saying, I don't know, if connector.get AP, I think this is the correct one. Yeah, it seems like it. We could do analogWrite let red. I'm going to say, so I don't know, 100. analogWrite let blue 200, and analogWrite let green, I don't know, 50. So not a lot of green, Most of it is blue and some red in there, right? So we're really gonna make our own palette. I'm gonna remove these lines. I'm gonna hit upload, remove the, there we go. Upload complete, replace the capacitor. Here we go. Restart the connector, but first we select autopilot, AP, altitude lock. I'm gonna hit start. So if we did things correctly, the moment we hit the altitude lock, it should start to display our color. There are 2 altitude locks in here, a bit confusing perhaps. This is the actual value. Altitude lock on with the word boolean behind it is the on or off state. And here we go. It actually turned on. We didn't have any logic to turn it off. But right now it's still running, right? So if we hit it, it turns on. If you would just change these values, we could mix another color, whatever we'd like to create something else, because it's not really that clear, because it's most of it is blue with a little bit of red and a little bit of green. So it's a bit of mix and whatever you'd like to create your own colors. Now this takes up 3 pins, so that's quite intensive on your, especially if you're using a Uno. Perhaps if you're using a Mega, you've got more a range of pins available. So that's more easy to hook it up like this. There are some options to reduce the pins needed by using some kind of chip, I2C interfaces, whatever, to really reduce the amount of pins needed to control LEDs. So thank you very much for watching. I know it's been a long one. I want to give a special thank you to all my Patreon backers who make these videos possible. And of course, a special thank you to Andre and Sim Racing for You, for they are my top tier Patreon backers. So stay tuned for the update that is coming your way, and I hope to see you soon.